Now from Mindanao State University, General Santos City, let's hear from Mr. Mike Marave as he presents the research Photovoltaic Generation Forecasting using Autoregressive Integrated Moving Average with Support Vector Regression Hybrid Model.
I, Mike Marave, together with my co-researchers, Engineer Venusti Elevencionado, Julian K. Matundo, and Ivan Dave Torrecampo, greet you a pleasant morning. I am delighted to have the opportunity to present to you today as we go through a topic that sits at the crossroads of technology, energy, and environment. The subject of our research revolves around a crucial aspect of transition to a sustainable energy future, the solar photovoltaic forecasting. In an era where renewable energy sources are taking the center stage, the ability to predict solar energy generation with precision holds great significance. So let me introduce our study, a synergistic forecasting of photovoltaic generation, unifying autoregressive integrated moving average, or ARIMA, and support vector regression, SVR, in a hybrid predictive model. Through this presentation, we will navigate through the landscape of solar PV forecasting, exploring its methodologies, analyses, and real-world applications. So moving forward, but before that, we would like to express our gratitude to Project SINAG for their invaluable contributions to this research. Solar energy harnessed through photovoltaic systems has emerged as a frontrunner in our quest for cleaner and more abundant energy sources. However, the inherently intermittent nature of sunlight poses a unique challenge to its seamless integration into our power grids. This challenge necessitates innovative solutions that bridge the gap between energy supply and demand. In this study, seeks to construct the autoregressive integrated moving average model using the Python programming language. Then it will be optimized using support vector regression to help predict the irradiance values more accurately, which was measured using mean absolute error and root mean squared error. Next slide, please. Our study was greatly influenced by the study conducted by Sir Ian Benitez and Ma'am Jessa Ibanez and their co-researchers on Cerimax. Their study significantly shaped the direction and depth of our research. Ma'am, sir, thank you. In our methodology, you have considered 10 weather parameters, the PV production data, and irradiance data. For our data pre-processing, we've done data resampling, identifying the data gaps and data stationarity, then proceeding to the ARIMA SVR modeling through Python programming, and test the accuracy through RMSE and MAE to the final model and then forecasting. Next slide. The augmented Dickey Fuller or ADF test is used for analyzation and evaluation of stationarity of data. Determining its stationarity helps in selecting suitable model for data analysis. Evidently, the pattern of the series shows no trend and it alters in a consistent manner. Hence, we can use regression analysis for this data. Moving forward, the data used is from May 26, 2019, and the actual output was plotted against the predicted output of the same day to present their variation. Both trend of the PV output increases starting from 5 a.m. The inclination of the graph continues until around 10 a.m. where PV output generates the most power and proceeds to decrease afterwards up until 5 p.m. Between 6 and 4 a.m., no output is generated since there is no sunlight at these hours. Evidently, the trend could be interpreted as good fit. The table above shows the computed value of the root mean squared error and the mean average error, which can be seen at the next slide. Comparing the model's prediction and the actual values, the result on the table indicates accuracy of the model used, with RMSE having a value of 3.04 suggests that an error of 3.04 was made by the model on the average prediction in comparison to the actual values. Meanwhile, the MAE results to 2.19 MAE indicates the magnitude error created by the model. This means that between the predicted values and the actual values, there is a 2.19 average absolute difference. The lower the value of error, the better the performance of the model. And these results indicate that ARIMA SVR hybrid model demonstrate a high level of accuracy in forecasting as evidenced by the model's remarkably low error value. In the table, go back. In the table, the high forecasting accuracy achieved by the ARIMA SVR hybrid model signifies its reliability and suitability for forecasting. Next slide. The contribution and innovation of this study, number one, is the study proposed and conducted an assessment of the performance of a hybrid model based on ARIMA and SVR. The results show that ARIMA SVR model produced a very low MAE of 2.19 and the RMSE of 3.04, indicating high forecasting accuracy when compared to a single ARIMA model. The hybrid model proved to be more robust and effective. And third, the integration of solar PV into the grid can be accomplished successfully by employing the ARIMA SVR hybrid model for generating accurate forecasts. Of course, this is subject for further research. And for our conclusions, the findings of this study reveal that ARIMA SVR hybrid model performed exceptionally well in terms of forecasting accuracy. Again, this was evidenced by the remarkably low error value obtained from the model, and the high forecasting accuracy achieved by ARIMA SVR hybrid model signifies reliability and suitability as forecasting tool for PV generation. And that ends my presentation. Thank you very much.
Thank you, Mike.